Hi everybody, I'm just going to give you welcome to the 2017 Exemplar Homes Tour, and run by SUPERHOME movement with the kind support from the Christchurch City Council. I'm just going to give a little rundown on the details of this house and some of the key features. And how's everybody finding the tour? Has anybody been to the other houses so far? Cool. So there's a good range of homes available to look at this year. There's about 10 homes in total, and they're all quite different. So there's some large homes, small homes, all varying different sort of levels of performance and different features. So that's really good. So, and a range of sort of price ranges too. So this house here is probably sort of mid to high, and there's some more affordable homes as well. So this house here is probably sort of 3,000-ish, and a square metre to build. And there's homes that are sort of low 2,000s a square metre. There's a nice one out in New Brighton, which is a good example of an affordable but energy efficient high performance home. So there's this is a bit more architectural, so there's a bit more going on here with the different kind of volumes and the high ceilings and things. And some of the materials are a bit more high end than a normal home. But yeah, I think it's really good that there's so much interest in the tour, because we really need to be building better homes in New Zealand. So the typical New Zealand building code house is about 3 stars on the Home Star rating. This home here, I haven't quite finished putting it through the software, but I think it's probably around about an 8 or a 9 on the Home Star scale. And in some ways it's better than the 10-star home, which was one of the homes on the tour last year, because we've just learnt and we've improved some of the details. So each home that we do, it's kind of like a prototype, and we learn better ways of doing things, or more cost-efficient ways of doing things. So I jokingly say this should be the 11-star home, this one. But there is no such thing as an 11-star home. But yeah, so we've really tried to follow sort of passive house building methodology, or there's different ways of doing that, but here we've done off-site airtight wall panels. So basically whole walls are made in a factory, they're put onto a truck and delivered to site, and then there's a crane, a high ab on the back of the truck, so they just put the walls into place. Similar with the ceiling, they were made to the roof, structural roof panels, which we can see here, which we're actually utilising the panels as our finished ceiling. So that's a 100mm thick structural panel. There's 90mm of foam on top of that for insulation, rigid foam, and then membrane and battens in 2 directions. So we've got a ventilated space there between the metal roof and the insulation layer. So this is probably one of the first houses we've done this, and it's quite good. So I like the look, but also it's our structural roof, and really strong, really good in an earthquake. We don't have to worry about jib cracking and coming back and repairing it. So it's good from that point of view. And again, everything just arrived on a truck, and one day, I think they started on Tuesday. We got the wall panels, the roof panels, the few steel beams that we needed, and the windows, everything here. A whole bunch of trucks turned up, and slab was already down. It had gone down the weekend before, and by Thursday afternoon, 2.5 days, they had the roof on. So everything was watertight and nothing getting wet out in the rain. So typical construction, you see houses with timber framing sitting for weeks or months, rain affecting it, and you've got to wonder what happens to all that moisture, and particularly if it gets enclosed quickly and not allowed time to dry out depending on weather. So another good thing is everything's dry, everything's high quality, and if it happens quickly, it'll be saving some cost too. So less time on site, less cost. Scaffold, it's quite expensive to hire scaffold in New Zealand, so yeah, less scaffold time. So what we did here is we've got quite a large overhang on the roof, and you can see the roof panels cantilever out, and so we could achieve that with this panel. It's quite structural. And up at the corners we've got a cantilever in two directions there, so we've just got a little box section of steel that sits on top on the window line. So normally you'd have a beam above the window, or a lintel it's called. So here it's kind of like, looks like there's some magic there, there's no lintel. And it looks like the roof's just floating and there's nothing holding it up, but there's actually a little bit of steel on top of there. So the panel has insulation above the space that we're in, but the insulation stops at the window, and there's nothing where the roof sort of floats out over the eaves on the outside. But those eaves are really important because they stop the house from overheating. So with our thicker walls and with our good construction and our fully insulated floor slab and the high performance windows, we can quite easily make a warm, energy efficient house, but it's actually more difficult to keep it cool. And there's no cooling required in here because we've thought about the windows and the shading, and that's critical. You know, the other thing about the windows is just, yeah, we've recessed the windows. So if you look out on the deck there, or most of the doors there, inward opening, there's quite a thick return with the doors recessed back in. So that's partly because we want to have the windows in the warm part of the wall, and even the windows are also recessed, but to a lesser extent. So it's standard practice in a lot of overseas countries, Europe and European countries and that, where they're recessing the windows. In New Zealand it's practically never done. So it's standard to have the windows flush, overlapping the external cladding. So just thinking about that, I might have a drawing of that. So the thing about that is, if the windows are out here, so this is a drawing of this house, but normally the windows are out flush, then that's a cold space. So there's a cavity in behind the cladding, and you can see it here on this wall too. We've got the battens there, and then the cedar cladding goes on the outside of that. That's just a requirement that we have to have that. So the reason that's there is for ventilation and for drainage. And so there's always cold air in there. There's sometimes moisture in there, possibly. And that's where, in a typical building code window installation, that's where your windows go. So there's no protection from heat loss. So there's a big thermal bridge there. So with this one here, this here is how we did the 10-star home that I mentioned. We recessed the windows into the wall. This is a European detail with a more heavily recessed window, so there's a big recess there. So this is more like what we've done with the doors here. We've heavily recessed the doors. So the key thing there is, yeah, bringing the window into the warm part of the wall. So the window's going to work better. And interestingly, you know, the brand's research shows that they did some research on, I think, 300 homes, and 299 of the 300 homes had typical double glazed aluminium windows, flush, overlapping the cladding. So the problem in New Zealand is people are building to code, and they're using the building code as a target, and it's really not fit for purpose. It's really unsatisfactory. So what we're trying to do with the SUPERHOME movement is show that we need to do much better, and it's actually not a lot more expensive to do a much better, high performance, energy efficient, healthy home. So yeah, the other thing is, other than recessing the windows, is what is the window. So I mean, in this model here we're showing a 3-pane triple glazed window. So that is standard overseas. So in New Zealand, it's we're not doing that. We're doing double glazing, and we're not really set up to do the triple glazing. And so if we do triple glazing, normally we're importing the windows. And yeah, so but there's double glazing and there's double glazing. So this house here has double glazed windows, but they're about 4 times as good as normal aluminium double glazed windows, and there's a number of reasons for that. So the first one, which is really most of the major glazing companies, they're putting a metal spacer between the pieces of glass. So, the super spacer is a plastic one, so there's no point in having fantastic windows installed properly and then putting a piece of metal between the glass, because that's just thermal conductivity. So it's relatively cheap to do that, but I don't know why they don't just do that standard. You've actually got to ask for that. So these windows have PVC frames. So there's 3 different companies now that do the PVC frame windows, and so that's relatively new in New Zealand, and whereas that's probably the majority of windows, or definitely the majority of windows in other countries, are PVC, not aluminium. So New Zealand, we're a bit of an oddity in a lot of regards in how we build, and one of the things that is unique is 95% of our windows are aluminium, whereas other countries see that as a really poor performing material for a window frame. So PVC is better because there's less thermal conductivity. There's no issue with the UV, which is a common sort of urban myth. And interestingly, one of the major aluminium window manufacturing companies has just set up a plant in Christchurch to make PVC windows. So the whole idea that they're going to break down and get brittle and disintegrate in our UV environment is a bit of a myth, which is a bit funny. So, the material that these windows are made out of is quite different to the old sort of Marley rainwater gutters that, So the next thing is the glass. So the glass is a much bigger area than the frame. So, if you can do high performance glass, then that's going to have a big impact. So low E glass is really important. So there's 3 different levels of low E. So this house has low E XL, which is the best one. So that gives you 30% better performance. So that's huge. So argon gas. So what did I just do? I just turned that off. So a lot of people talk about argon gas. It's only has a sort of little bit of increase in performance, so 10% better. But it's actually cheap, so we just do that as a matter of course. It's just injecting a little bit of gas that's heavier than air into the insulated glazing unit, and that's not difficult. So a good PVC window is 0.53, the R value, thermal value. An aluminium window is 0.26, double glazed aluminium window. So these windows here are 0.7 because we've done those things that I just talked about. So you could do better than that even, you could do triple glazing and also do those things. And you could get to more than 1 on the R value scale. So, it costs more for better windows, but it is really important because I really look at the windows as a hole in the wall, because basically that's the weakest link. It's 1/10 of the thermal value of the wall, and that's where most of the heat loss is going to be, out the window. But other than that, just designing the house so that you've got the windows in the right places. So there's very few windows on the south side normally. that's what you're trying to achieve, unless you've got a view to the south side, and it gets a bit problematic. But and most of the glazing on the north side, but you can have too much, so you've got to be careful about overheating if you haven't got the right shading, which I already talked about, and also heat loss. So if you've got too much glass, whether it's whatever elevation it's on, whether it's on the north, whatever, then you're also going to have too much heat loss. So you've just got to be very careful about the size and orientation of the openings. And you know, in some cases there might need to be more than a roof overhang to get the correct shading. You might need shutters to get the correct shading. Okay, so my favourite topic, windows. So I haven't really talked about this wall.
How does thermally broken and PVC compare?
Performance or cost? So performance, the PVC is better. Cost-wise, they're about the same.
Okay.
Yeah.
Who's the company that's produced PVC here?
There's UPVC windows. There's these windows. NK windows. There's some brochures for them here. This model here is an NK window, and then there's also another new company in the market, APL, and they've been set up locally to do PVC windows too. So there's a bit more choice, so that's good. So for a long time there was just one company and it was always more expensive, but that's changing.
So is it satisfied local standard for the window? For a new window?
Yeah, these windows I'm talking about far exceed the standards. Yeah.
So but you have to approve it by the local city council?
Yeah, there's no problem with that. They've all got their various sort of testing and approvals that are required, and go through building consent, no problem. Yeah.
We can just use it.
Sorry?
We can just use it.
Yeah. But the key thing is the details. So sometimes, if, you know, someone hasn't seen the recessed detail, there's a few questions about that. But once you explain it to them, they're okay with it. And I guess the thing about having the windows flush, and why everybody does that, is because that is the standard building code detail, and the reason people don't deviate from that is they're scared of liability, you know, and we've had the little thing called the leaky building syndrome, and people don't want to do anything different to the building code detail. And it was probably outdated when it was introduced to the building code 15 years ago, but it's a detail that's probably, in terms of international best practice, it's about 25 years out of date, and that's just the way we've always kept doing the windows in New Zealand. So we're probably a good 15 to 20 years behind other countries in how we're building. So another important thing is the wall. So here I've got a sample of the wall construction in this house, and I'll just go back a step to the wall. So here we've got the physical model of the wall. On the screen here we've got the drawing of the wall. So these are made off-site, like I've already mentioned, but you could do the same thing a bit more traditionally with frames delivered to the site and make it pretty much on-site. So this here, as you see it, this is how it arrives, with the plywood on the outside. The insulation's already in there, it's put in the factory. It's got a proper high-performance membrane on the outside, European membrane, and then it's got a airtightness membrane on the inside, so that is really important. So New Zealand houses don't have an airtightness membrane, generally, 99% of them. And then the other thing here is we've got a services cavity on the inside. So we've got 140 millimetres of airtight sheep's wool insulation. It's really important that it's airtight, but I'll come back to that. And then on the inside we've got a 50mm cavity, which is also insulated, but that's where our plumbing and our wiring and in this case we've got air ducts going through the wall too. So when you're putting in your services, your electrical wiring and your plumbing, you're not penetrating the airtight insulated layer. So yeah, and then afterwards we put the extra insulation in inside. So we've basically got 200mm thick insulation, and then we've got a 50mm cavity on the outside for the cladding. And normally that's 20mm, but here it's 50 because we don't want to penetrate that membrane with the fixings for the cedar. So that's a structural cavity batten, that's quite important. So because we've got that, we can just insulate the whole wall and we don't need any framing in there for fixing the cladding materials. So that's what we're calling the super wall, and that's the super window. So
Does it cost much more expensive than the rest?
well, if you do the thicker walls, it's going to be more expensive because there's more material. But surprisingly, the off-site construction and doing it that way isn't very much different to the traditional way of building. That's what we found anyway. And yeah, so basically the reason we're doing that, the importance of the airtight wall is twofold. First of all, if you're leaking air through the building, through the wall, or gaps, you know, or you've got windows that aren't as good as these windows, then that's like if you consider a normal house, typical New Zealand house, it's sort of 8 to 10 air changes. This house here is roughly 1, so we haven't done the final blow-up door test yet, but it'll be around about that. So that's 10 times the amount of air that is escaping out of the building, and that's 10 times the amount of air that you have to heat if you're heating the building. But that's not the biggest problem. The biggest problem is that if you've got air escaping through the wall, then you can have condensation in the wall, and that happens in new New Zealand homes. So inside the house we're showering, we're cooking, even just breathing at night in bed, you know, the reason there's condensation on the window is because you've got moisture coming out of humans, you know, so a couple of people in a bedroom, there's a lot of moisture being created, and where does that go? So this membrane stops that moisture getting into your wall and forming condensation inside your wall. So the condensation will occur probably somewhere within that wall, because as the temperature of the air drops, it loses its ability to hold the moisture. And if you've got condensation in your wall, and it's the optimum temperature is like 12.5 degrees for mould to grow, then you have an environment where you've got black mould in your wall, and that's a big problem. So 2 reasons for that membrane and that type of construction. There's probably a third actually. Like if you think about the insulation in the wall, it's going to work much, much better if it's airtight, because if you sort of use the analogy of a woolen sweater, if you're out in the wind, you're going to be much warmer with a woolen sweater with a parka, windbreak parka over the top of it. Same with your insulation in your wall. If you poke lots of holes in your wall where you're putting power points and wiring and stuff, then it's just not going to perform anywhere near as well as if it's airtight, the insulation. So that's the main things with this house. The other thing, well, probably the really important thing is we've insulated not only under the slab but up the edge of the slab. And because we've got thicker walls, we can run the insulation right up to the bottom of the wall. That's really important. And we've heated the floor with hot water. So basically we've got an air-to-water heat pump. It's powered by the solar panels on the roof. It heats the water for both the floor and the domestic hot water cylinder. It's a bigger than normal hot water cylinder. And that system basically means that we can take free solar power, convert that into heat that we store in the building. So we're storing it in the hot water, which is a really good storage medium for thermal, and then we're also storing it in the concrete, which is also good. So basically we're using the building as a battery, and instead of feeding the power back to the grid, we're actually using the power and storing the power. So I think the government, you know, ECA have their calculator and they talk about how solar doesn't really pay off, and it's just because they're not thinking about how to use it properly. So they think about what do you get back, what's the feedback tariff from the power company. It's actually pretty low. So that's really one-dimensional. They need to look at the whole equation and what happens if you build a house which is A, better at holding the heat and not going to leak heat, so it needs less energy for a start, and then it can also store energy as well. And then the next thing is batteries. So this house, I'm not sure if there's going to be batteries for this house, but the 10-star house had batteries. So even the power that is used at night for the fridge and the lighting and whatever's plugged in is solar. Also in this house we're collecting the rainwater from the roof, and we've got energy drains on the bathroom, so when you're having a shower you have 38 degrees water going down the drain. We're taking the heat energy out of that and transferring that into the supply water that's going up to the shower mixer. What have I forgotten? The lighting. So we've got beautiful LED lighting which is really energy efficient, and we've put a lot of thought into the lighting. So the lighting, Nikki here is the expert on the lighting from the electrical supply company, and there's some other examples of lights over there. But key thing is surface mount, so we're not putting holes in the thermal envelope. We do a lot of uplighting and surface lighting. What else have I forgotten? Probably lots. There's a lot to think about in doing a new house. There is a little brochure here with the key points on it. So you're welcome to grab one of these and ask me any questions just in case I've forgotten about something. So all of the materials are all environmentally sound. The paints are from Natural Paint Company, no VOCs. So it's a very healthy environment. We've also got a really good energy recovery ventilation system. So that's really been cleverly hidden in the building. So we've got air ducts under the floor, embedded in the concrete floor, and there's actually supply air comes out underneath this island bench, and the extraction is up at the back of the mezzanine floor up here, and we're extracting from the bathrooms and laundry and supplying fresh air into the bedrooms. If you look closely you'll see little vents on the walls because the ceiling is wood. Can't get the air in the ceiling, so we put it through the walls and through the floor. And that's a proper energy recovery system. So it's taking the heat energy out of the extract air and preheating the cooler fresh air that's coming into the building, and it's 95% efficient. So that's just on all the time, and it's continually changing the air. So there's no sort of new house smell with materials and things, and it's always really, really high air quality. So that's the other thing with New Zealand homes, there's really, really poor air quality, which people don't think about.
So are there filters or something you need to change?
Yep, you have to change a filter once a year, but it's not expensive to do that. You can do it yourself, or you can get someone to do it if you want to.
Is it somewhere convenient to get at?
Yep, yep. So normally there's just a panel in the ceiling, and you just take that out. So what else have I forgotten? Probably lots.
For the you're saying using the solar panel on the roof to pay the water and pour the water light into the concrete slab to heat up the concrete. But how about in the winter where there's not much sun or it's quite cold? Do you have a say like using the electricity to heat the water?
Yeah, so we're not using thermal solar, so that's an important point. So the old solar hot water, either with the panels or the tubes, that's really we used to do loads of that, but now that we've got PV, solar electric, we don't do that at all, so that's a bit of a dinosaur now. So we're not really relying on heat energy from the sun, it's more about light. So the PV panels, they're going to work even if it's not a bright sunny day, and they're gonna they'll work better in summer because we've got more sunlight hours, but they're still going to work in the winter. And then if we do have a situation where there's a storm and there's no sun for a week or whatever, there is electrical backup. So there's an electric heat pump anyway. It's just that heat pump is using the solar power when it's available. So there's no problem there with that. And yeah, I think the key to this house isn't just what the technologies are, but it's how they're integrated. So you can have a list of ingredients, but it's really about the recipe, about how you put it all together, and how some of these existing technologies that are not new, how they're integrated together to work better, and how they fit into the whole overall holistic house design. Does that make sense? So so you need to think about everything together rather than just tick the box, yeah, I've got solar, yeah, but how's that solar working? If you're just feeding it back to the grid and not utilising it in the best way, then it's not going to work for you as well as it could. The other thing too is this system that we're using here with the hot water in the floor and heating the hot water as well, the dual system via the solar, probably wouldn't work as well or definitely wouldn't work as well in a normal house, because in this house here we're not leaking heat, we've got thicker walls, we've got high performance windows, everything's better, we've got the insulated floor, so the amount of energy required for this house is much less than a normal house. So in actual fact the temperature of the water that is circulated through the floor is much lower. So this house here, it still hasn't got the power turned on, so the heating system was just turned on this morning, so it's not really up to temperature yet. So normally it'd be much warmer than this, and the floor would be much warmer. So if you come back next week, it'll all be finished and it'll be warmer. But yeah, I think where was I going with that? Yeah, I think the temperature of this water going through the floor is probably sort of early 20s. Whereas if you had a normal house, which was nowhere near as good and leaked a lot more heat, you might need 35 degrees or 40 degrees water going through the floor. And that's going to use a whole heap more energy, and it's going to need probably a different bunch of equipment. So basically our heat pump's much smaller, so it's a cheaper capital cost for the heating system because we need less heat in the first place. So put more into the fabric of the building, put less into the heating plant, and it just works much more efficiently as well. So yeah.
Can you talk about the recessed in of the windows from the external wall surface? What's the reason? I mean, of course you say this is a sort of better way to do that, but why typically?
It's really just about the heat loss. So, and it looks better too, but there's a reason that it's standard overseas to recess the windows. And so if I just get the right one up here, I've got so this is basically the drawing from the building code, and I already talked about this, but that's your cold part of the wall, that's where your window is. That there is, well, that's actually the 10-star home. We've recessed the windows more in this building, but so your window, PVC window, not aluminium, and it's in the warm part of the wall. So that makes a big difference.
So basically, actually, sort of set back from the cold part of the environment.
Yeah, so if we look at this one here, this point here, there's kind of a huge thermal bridge here. So there's lots of cold transmitting through there. There's a big chunk of aluminium there. So that's a highway for the energy there, and that doesn't exist in this one. So even with the typical New Zealand window installation, you've got to have this big structural support bar underneath the window, otherwise there's nothing supporting the weight of the window, and that's quite chunky. It's a piece of aluminium. It's also really good heat sink. So we don't need any of that here because we're just putting the window on the frame. It's structurally supported on the frame. Questions? Hopefully I've explained.
So how much, say if you compare the, say like construction time, say the wall panel is sort of really nice from transport on the side. Is that how much faster than the normal way?
Well, it took 2.5 days from slab down to roof on. Yeah, it's quite different, the construction time.
Because they say like wall frame, also like really made from the factory. They say like good at overall construction time is about the same. But the panel is basically much better.
Yeah, I think this is pretty much a complete wall. There's a lot more work to be done once your traditional frames get stood on site. The next stage on from this, which we were planning on doing with this house here, was install the windows before the walls come to the site as well.
So it's the whole wall comes.
Yeah.
Yeah. 2.5 days pretty quick. The other comparison